Recording is rolling. It's Friday, April 10th. Yesterday I gave you guys the DC circuit slab, so we're just gonna pick up from there and also I'll help you guys out a little bit more on this page. So we're just doing more circuits, schematic diagrams, multimeters, the whole thing. Okay, and we got a split play going on here.
Oh, yeah.
Right, so I want to give you guys as much class time as possible to do more of that. There were a few of you guys to finish all three schematic diagrams. So often if you did. I did one model with you guys, and then let you guys put one here and one here. Oh, you don't have to do all the rows. You don't have to use too many resistors if it's too difficult. That's okay. Okay. But I'm looking for different setups that you do. Right. Right. So here, do a example with you guys. All right. Let's look at this one right here. You guys see this one? Okay. No, there are lots of different versions of the paper, so you might have different numbers, different voltages, whatever. Right. But everybody has this schematic for this one. It looks like, here's my battery right here. I'll construct this right in front of you guys. And it looks like we got one resistor called resistor D that, well, creates a closed loop with the battery. Okay. And then these other three resistors, A, B, and C, that are in series with each other and in parallel with that resistor D. And so what that could look like is if you tie together 4 Christmas lights like this, and then attach these 2 leads right here to the leads of the battery. Okay. Oh, guys, before I connect it, since all these resistors are approximately the same resistance, what do you think the brightnesses of these bulbs are going to look like? Like, guys, do you think these 3 will look identical to each other? Yeah, guys, raise your hand if you think these 3 will look like the same brightness as each other. Yeah, because they're all in the same branch and series with each other, same resistance. Right? Now, what about this standalone guy right here? Is this guy going to be the same brightness, way brighter, or way dimmer than the other 3?
Way brighter.
You guys are saying brighter? Yeah. Raise your hand if you say brighter. If you think brighter. Yeah. Well, why do you say brighter?
That's terrible.
Yeah. Here's the way I would think of it: it's here. I have a 9-volt battery. Isn't this gonna get all 9 volts across it? Versus these other guys, well, they collectively get the 9 volts, but it'd be 3 volts and 3 volts and 3 volts. So it's a little bit at a time. Right? That's one way. Right? Let's see what this actually looks like. Right, you guys ready? Let's see if you guys are right. Oh, yeah, look at that. Right. This one right here, if I flip it over here, it looks just like the picture. Right? Yeah, that one's really bright. This resistor D is really bright. And these other 3 in series with each other, fairly dimmer. Is that it? All right. So you guys, of course, have those materials. I also have a box of multimeters over here. So if you guys get your hands on one of these multimeters, here, I got a whole box here. You got later for the lab, but here, we'll at least do this table with you guys right here. So you guys just saw me construct this, saw exactly what it looked like. Now, the numbers on this page here. Let me see if I can boost this up a bit. Let's see, get this closer to the camera. I'm really just focused on this quarter. Yeah, I think that looks better. Okay. So according to this page, I have an 18-volt battery. Right? So let's say this is 18 volts right here. 18 volts. Okay. Now on your page, if you're lucky, maybe you also have 18 volts like I do, or you might have something different. Okay? And I gave you all these resistors, and I told you each resistor in ohms. Something like that. Okay, so how do you do this? I'd like to make a waterfall model so I can get a 3-dimensional look at this. Okay? Right, so I think resistors C, B, and A, one after another, be like splash, splash, splash. Right, 3 waterfalls in series, one after another. Okay, and then this resistor D that was really bright, well, that's kind of like a splash, like one giant waterfall way out here. And then, of course, they route back to the pump. Let's say back to the battery. Around they go. Okay. Now, then this waterfall analogy. What does the height of the waterfall represent again?
Voltage.
Yeah, voltage drop. Voltage drop. So the battery in this case is so many volts. And I usually don't know the level of detail of like creating skinny and wide waterfalls, but if I did, that could be proportional to the current in amps. Okay. All right, let's find out what's the total equivalent resistance. Well, this is where we have to go through this process. Do you guys remember we do this process where we find where's the voltage, which is on the left side. Then we fly over to the complete opposite side of the circuit and find equivalent resistances all the way back. So how about these 3 in series? Can I very simply add those together? Is that right? Can we simply add those together? So I'm going to draw an equivalent circuit right here. So be looking like this. Here's my battery, 18 volts. This resistor D is 9 ohms. Okay. But these 3, I have 10, 4, and 4. Guys, what's 10 plus 4 plus 4? 18. So I have 18 ohms right here. Okay. Okay, so guys, is the circuit the equivalent? Same thing. Okay. This battery feels like it's pushing against the same total resistance. And what is that total resistance? Well, that's the next step. 18 volts. Okay. Now these two resistors are in what with each other? Series or parallel? Parallel. And how do you solve parallel resistors? It's a fraction. Whatever what? Pro-
R1
product
over
product over
some.
product over sum. You guys remember that?
Yeah.
Like two in parallel. Right? If you and a friend are painting a fence together, and it takes you so many hours and your friend so many hours, you need a product over sum to figure out the total time together. Right? And then resistors, same idea. So this equivalent resistance right here is 18 times 9 over 18 plus 9. Hey, if it took you 18 hours to do a task and your friend 9 hours to do the same task, and you work together, should it take you, take a guess. How many hours would it take you to complete the task together? It takes you 18 hours by yourself, your friend 9 hours by himself. Together, it takes how long?
Half the time.
6. Right, 6 hours, or in this case with the resistor, 6 ohms. Does that seem about right? I think it sounds right? Because collectively you would be faster than your friend alone. Okay, is that okay? And are you guys good with that now? Okay. And you guys did the numbers for your paper? Okay, which means I can know this box right here. The equivalent resistance of my entire circuit is 6 ohms. It's as if all these resistors are collectively conspiring to act as a giant 6 ohm resistor. Okay, 6 ohms. Right, is that okay? Right, now what? Let's do, how about this? Let's do Ohm's law and then Joule's law of the point of the battery. So Ohm's law. Can I say Ohm's law, Ohm's law, Ohm's law? Can I say current equals voltage over resistance, I equals V over R? Okay. And I have an 18-volt battery that was given, 18 volts. And it's collectively pushing against pushing against 6 collective ohms of resistance. That's what I found up here. Okay. Guys, how many amps is that? That's 3 amps. You guys see 3 amps? Okay. And if you ran the numbers on your paper, you should be getting whole numbers for every single cell. Are you guys only getting whole numbers? Nobody should be getting any decimals. Is that right? So I just got 3 amps right here. Okay. Actually, this very last cell I'm going to come back to at the very end of this table. Let's come back to that. Okay. All right, let's figure out the voltage drops. Oh, actually, this waterfall model, I can immediately see one of the voltage drops. Guys, what's my voltage drop across my resistor D? Is it the same as the battery?
Yeah.
Yeah, because that's a closed loop right there. That's Kirchhoff loop rule. So I go to resistor D and say the voltage drop across D must be exactly the same as the battery because it's closed loop. Right, my waterfall model is the same elevation, blah, blah. Okay. Okay, now, here's where it gets a little trickier. Oh, you know what? Do it. Because there's multiple different ways to correctly finish this table. Do you guys remember that one? Here, I have something in mind. Let me see if I can. Here it is. I'm thinking of a particular poster I want to dig out. Okay. Good. If you could use any of these rules to fill out the rest of the table. You guys remember Kirchhoff's rules? Right. No, technically there's only 2 Kirchhoff rules. There's the loop rule and the junction rule. Right. But all these other rules kind of fall out of those rules. You guys remember that? Right. How does current split? How does voltage drop? Blah, blah, blah. Right. There are easier ways and harder ways to complete the rest of this table. Right. Let's do one way. Let's do Ohm's law at the point of resistor D, because I know the voltage drop in the resistance at resistor D. So can I just do V over R, just like I did down here? That 18 over 6 was 3. Because what's 18 divided by 9? 2? Isn't that like 2 amps? Right, so I know 2 amps are going through a resistor D. Is that okay? 2 amps through a resistor D? Now, if that's true, 3 amps left the battery. 3 amps left the battery. Then 2 amps cut right and go through resistor D. Oh, so how many amps must have gone the other way? Let me say it a different way. 3 cars leave the parking garage. 2 cars turn right and go down this street. How many cars go down the other street? 1. And doesn't that apply to all the other resistors? Okay. It's the same answer. Yeah. Okay, well, all the current can go through this one. Right. The only way for that to happen is if these were added up to like 1,000,000 ohms, and then like 99.9% of the current could go through that one. But do it in a few minutes. I can walk around and look at your paper. Okay, do that. All right, so let's do Ohm's law, but rearrange. Actually, a lot of textbooks write Ohm's law in its non-fraction form. They write voltage is current times resistance. Is that also Ohm's law? Just rearranged a little bit. Okay. And that happens to be really handy for what we're about to do right here. Because I have I and I have R. I times R. Hey, can I just do I times R and get this V right here? Okay. So that looks like 10 volts here, 4 volts here, 4 volts here. Okay. And since that's part of a loop with the battery, guys, what's 10 plus 4 plus 4? 18. Ah, which matches the battery, which it had to because that's the outside loop. That's Kirchhoff's loop rule on this whole outside loop. Ah. Okay. Okay. Finally, we haven't touched Joule's law yet today. Let's do Joule's law. One version is power is current times voltage. Alternately, you can go power is current squared times resistance or voltage squared divided by resistance. They'll all get you the same answer. Let's just pick one of these and run with it. So current times voltage. Can I do 18 times 2 is what? 36, and that'd be 36 watts. 36 watts is that light bulb. What's 10 times 1? 10 watts. What's 4 times 1? 4 watts, and then also 4 watts. Okay. Finally, is that okay? I just did this roll over and over, but you could have done either of the others. They still get these same number of watts. Okay. This very last cell, there are two perspectives I'm going to do on this very last cell. Two perspectives. One is I could apply Joule's law at the point of the battery. Guys, could I say 18 times 3? What is 18 times 3? 54. 54 watts. Okay. Now, so the battery is supplying 54 watts. That's 54 joules per second. That is how fast this battery is being drained. It's losing energy that fast. Okay. Or here's the other perspective. Does supply have to match demand? Because this is a supply of power, 54 watts. What was the demand for power? Let's see. I have these numbers right here. Let's see. It should be the same thing. But it's 36 plus 10 plus 4 plus 4. Get that out of the glare. Hey, it's 54. It's the same thing. It's the same thing. So guys, if you do the table completely correctly, then by the time you get to that last cell, you should be able to either by Joule's law or supply and demand get the exact same number of watts, just like I did. Right, guys? Good? All right. So, again, continuation from yesterday. Because you didn't really have a reasonable amount of time yesterday to finish the whole lab. So, yeah, you guys have all the materials. Today's okay. Here's our agenda. All right, you guys got batteries. You guys got bulbs. You guys got multimeters. You guys have lab tables. You have all the materials you need. And then if you finish it yesterday, then do it. You can work on these with your friends, and yeah, try to get them. Eventually, you got to pick up this paper anyway, but not till after the weekend. Okay. All right, so I will walk around and help guys out.